In this video, we define Euler's phi function and obtain a formula for Euler's phi function. Euler's phi function is suppose we are given a number n, then Euler's phi function is denoted as phi of n is defined to be the number of integers less than n and relatively prime to n. For example, if we consider the number 30, so capital N is taken as 30, and that obviously can written as 2 into 3 into 5. Now we will consider 3 sets. We have 3 prime numbers, so we consider these 3 sets. Let A1 denote the set of all numbers which are divisible by 2. And then A2 denotes the number of, the set of all numbers divisible by 3 in 30, and A3 the set of all numbers divisible by 5 in 30. Now this list, that is when we list it out, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, all are multiples of 2, so they are all divisible by 2, and the number of such numbers, that is order of A1, that is they are 15 in number, so we have 15, and we note that this 15 is 30 divided by 2. And in the same way, for this we have the numbers which are divisible by 3, all multiples of 3. So we have this, and if we count them, they are 10 in number, and that 10 is written as 30 by 3. And the same way for this one, we have 6 numbers, so that is 30 by 5. Now if we want to find the set of all numbers in n which are divisible, n is here 30, divisible by both 2 and 3, then in that case 6, 12, 18, 24, 13 that we have. So the number of elements in the intersection gives us 5, and again we notice that this is nothing but 30 divided by 2 into 3. So in the same way for A2 intersection A3 we have number of numbers, the set of all numbers in n divisible by both 3 and 5, and that's given by 15 and 30, and the number of numbers in n, that is 30, divisible by both 3 and 5 is given by just 2, and that is 30 divided by 3 into 5. Similarly, for the last one, 5 and 2 we have, so 10, 20, 30 only that we have. So the number of elements divisible by both 5 and 2 is just 3, and we notice that is 30 divided by 5 into 2. And finally, we want to find those set of numbers in n which are divisible by 2, 3, 5. So it is only 30. So the number of elements in that is 1, and again we notice that it is 30 divided by 2, 3 and 5, that is 2 into 3 into 5. Now we borrow this result by inclusion and exclusion principle. The number of numbers divisible by 2, 3 and 5, which is the order of A1 union A2 union A3, is order of A1 plus A2 plus order of A3, order of A1 plus order of A2 plus order of A3 minus of order of A1 intersection A2 plus order of A2 intersection A3 plus order of A3 intersection A1. Then it is first plus minus plus the order of the intersection. So in this case it is 15 plus 10 plus 6, so that is 31, and then 5 plus 2 plus 3, so we have 10, and then here 1. So when we simplify, we get that to be 22. But this one gives the number of numbers which are divisible by 2, 3 and 5. So we want to find those numbers which are relatively prime to n. So in the total 30 numbers, these numbers are divisible by 2, 3 and 5 means they are not relatively prime. our aim is to find those numbers which are relatively prime. So from the total number of numbers, namely 30, if we subtract this number, then what is required we will get. So n minus this order, that is 30 minus 22 here, and that gives 8. Now this is the basic concept used in finding a formula for Euler's phi function whenever n is given as any number which is written as p power a, q power b, r power c. So we will consider the general case. Suppose we have phi of n. Phi of n is considered, and that is given by this. The formula is this: p power a, q power b, r power c. It goes on, and 1 minus 1 by p into 1 minus 1 by q into 1 minus 1 by r, and so on. Now we establish the result when n is p power a, q power b, r power c, and that can be extended. So this result is proved for n equals p power a, q power b, r power c. As we did in the example, we write out a1, a2, a3, the set of all numbers in n divisible by p, and a2, the set of all numbers in n divisible by q. A3 denotes the set of all numbers in n divisible by r. So from this we can easily see that the order of a1, that is the number of numbers divisible by p, is given by n by p, and in the same way for the second it is n by q, in the third we have n by r. Now let a1 intersection a2 denote the set of all numbers in n divisible by both p and q. So the number of such numbers will be n by p into q. And the same way for the next one, it is the order is given by n by q into r, and for this it is n by r into p. And this one, a1 intersection a2 intersection a3, those set of all those numbers in n which are divisible by p, q as well as r. So we have the number of such numbers to be n by p into q into r. So again, by inclusion exclusion principle, the number of numbers divisible by p, q and r are given by, first we have plus, then minus, then plus. So we have order of a1 plus order of a2 plus order of a3 minus of order of a1 intersection a2 plus order of a2 intersection a3 plus order of a3 intersection a1, then plus order of a1 intersection a2 intersection a3. So we simply denote this by summation n by p, just one prime number p, q, r, like that. Here product of primes p, 2 at a time, p and q, and this one without the summation symbol, because we are considering only 3 terms. So we have this. So these are the numbers which are divisible by p, q, r. So these are the numbers which are divisible by p, q, r, p, q, r. But what we want to find is the number of numbers which are less than n and relatively prime to n, which are not divisible by p, q, r in n. So that means total numbers that we have, that is n. From that, these numbers, when we exclude, we get, this is the notation, this is the term that we have, and this is how you will have the right hand side. And in all these n is common, so that is taken out. So it is 1 minus summation 1 by p plus summation 1 by pq minus 1 by pqr. Here we don't have summation because we are considering only 3 terms. And this we have 1 minus 1 by p, 1 minus 1 by q, 1 minus 1 by r. If we multiply them all, this is what we arrive at. So this is rewritten in this way. Thus, we have phi of n to be p power a, q power b, r power c. This is for our n we have written, and whatever here we have, and that is given here. Now in this we also note one more thing, that if x is the divisor of n, it is accounted only once on the left side, only once on the left side. That is when we consider n, in this it is counted only once, any divisor. So now we'll have to ensure that it is also counted only once on the right side. So for which this is the explanation. If x is a divisor whose prime factors are just p and q, say. In this case we have p, q, r for 30, but the divisors, they will be say 2 and 3 in the case of 30. It can be just 2 and 3, or 3 into 5, or 2 into 5, or just 2 alone, or just 3 alone, or just 5 alone, or all the 3 together. So the divisor can be in those forms. So we have, if x is the divisor whose prime factors are p and q, say, then how many times does it occur? It occurs only 2 times, that is 2c 1 times in the first term. In the first term is this one. And once, that is 2c 2 times in this. And in the third term, it doesn't occur at all, p and q, because in the third one, p, q, r should be there. So here n by p plus n by q. So it occurs twice, and here it occurs only once, and here it doesn't occur at all. So totally how many times does it occur? Here 2, here 1, here 0. So 2 minus 1 plus 0, that is equal to 1. So it occurs only one time on the RHS also. So that can be seen with this example what we have already given there. So we have, we can see if we take in the place of P and Q 2 and 3. So in this 2 and 3 they occur. So that prime number occurs. We have 2 times that those numbers occurring, and in this case we have that is you consider the factor, 6 you consider. So it is not just 2 and 3, it is the divisor is 6. You are taking the divisor as 6, and for that 6 you have the prime factors 2 and 3. So 6 occurs in this as well as in this. We don't have 6 in this. So in these terms it occurs only twice. 6 occurs only twice. And how about in the rest, the next set? So it occurs only once, because you don't find 6 here. Here it is there, here and here you don't have 6. So it occurs only once. It occurs twice in the first term. These correspond to first term, these corresponds to second, and this one last. So we have 6 occurring twice. So we have written 2. And here 6 occurs only once, so we have written 1. And you don't have 6 in the last one at all, so we have 0. So this is in the case of 6 here with 2 and 3 as prime factors. Now in general, if x is a divisor of capital N with k prime factors, here we have only 2 prime factors. So 2c1, 2c2, like that we have. Now in general, if we have x to be any divisor with k prime factors, we do not actually know which is the divisor. So it may have only 3 prime factors, or it may have 4 prime factors, so we do not know. So in the general case, we take that this divisor has, say, k prime factors. Then it occurs on the right side. On the left side, that is, in this it occurs only once. In this it occurs only once. But on the right side, So in the first term, that is like this, when we write for the general case, it will occur Kc 1 times. And then here it will occur Kc 2 times. Plus, minus, like that it will go. Now what we do is, we are going to add and subtract 1 to this and take out minus sign from this. So minus into minus plus, that is what we have here. So minus sign is taken out and 1 is added and subtracted. So this is what we have, and this is actually nothing but this 1 is retained as such, and this is nothing but 1 minus 1 to the power k. When you binomially expand this, this is what you get. So it occurs 1 minus 0 times, that is 1 time. So we have even that part we have accounted, that is any term it occurs, any divisor occurs only once on the left side, and the same way only once on the right side also. So there is no repetition, it is only once it occurs. Now 5 of 30 already we got the answer as 8 by direct computation. Now we use the formula. Now we use this formula. Using that also we get this one, this 1 minus half. When you take LCM, it is 1 by 2, this is 2 by 3, and this is 4 by 5. So 2, 3, 5, they will get cancelled, giving just 1, 2 and 4, and that is 8. So this is how we find the formula for our phi of n, and using this section equations can be answered. But as such, this derivation may be asked, for which the proof has to be given like this. So in the next video we will see that some more results in elementary number theory.